Alright, welcome back. So in this video we're going to be talking about the basics of power. So power is another one of those terms that, like work, you already have a lot of kind of everyday ideas about it. And so we're going to kind of take that and run with it. So in physics, power is basically the rate at which work is done. So turning that into a mathematical statement, when we talk about average power, we're simply taking the amount of work done and dividing it by the total time. So one thing that's interesting about this is work is force times distance, and if we divide that by time, that's force times distance over time, and we know that distance over time is average speed. So the two main equations we're going to be using for power is its work over time or its force times average speed. So the units of power are going to be units of work, which are joules, divided by units of time, or seconds, and that's defined as the watt. So when you see a 60 watt or 100 watt light bulb, which are becoming more rare these days, everyone's using CFLs, but that refers to the energy that the light bulb emits in a certain period of time. So 100 watts is 100 joules a second. One example that I give is, remember I talked at one time about a quarter pounder with cheese, so there you go, there's a sandwich. Okay, so if this thing has a weight of 1 Newton, because that has a mass of 1 kilogram, if you move that up 1 meter to take a bite out of it in 1 second, that's basically 1 watt of power. It's taking a quarter pounder of cheese and moving it 1 meter in 1 second to take a bite. Okay, so another common unit for power is the horsepower. And so horsepower, basically 1 horsepower is the same thing as 746 watts. And sometimes we make use of this. For example, let's do an example problem. This is going to be, let's see here, number 103 on page 175. And this is a plane taking off. The plane has a mass of 3,250 kilograms. The plane reaches its cruising altitude in 12.5 minutes, which I converted into seconds by multiplying by 60, so 750 seconds. It reaches a height of 10.0 kilometers, and I'm going to turn that into 10,000 meters. And it's got a takeoff velocity or cruising velocity of 850 kilometers per hour, and I'm going to convert that into meters per second. If you're unsure about how to do this, take a look at chapter 1, and there's also a conversion chart on the inside cover. And then the power that this is supposed to give us, well, the plane is exerting 1,500 horsepower. And if each horsepower is 746 watts, that comes out to roughly 1.1 million watts of power. That's quite a lot of power. And what we want to find out is, given this information, how much of the 1,500 horsepower actually went into powering the plane. And this is kind of a weird concept, but most of the time things are not 100% efficient. If you put 100 joules of work into something, you won't necessarily get 100 joules out of it. And we're not really talking too much about simple machines, but here's just a quick example of how this applies to power. So basically we know that power is work over time. We know that the time is 750 seconds. The work, on the other hand, well, what work is involved to making this plane reach its cruising altitude of 10 kilometers? Well, the plane has two things that it's got to do. It's got to reach a certain speed, and we know that that takes kinetic energy. So we already talked about what kinetic energy is. And it also is going to have to go above the Earth's surface. So it's got to gain energy against gravity. So that's potential energy. So that's two different types of work that the plane has to do. It has to not only go faster, but it has to rise up into the air. And if we add those together and divide by the time, that's going to give us the power. Okay, so then kinetic energy is 1/2 mv squared. Potential, as we've talked about earlier, potential energy due to gravity is mgh, near the surface of the Earth, and 10 kilometers is not far enough to worry about. And then we divide by the time. And I'm not going to plug in all the numbers, you can do that later, but the power that we get from this is, well, we'll put it to you this way, it's about 4.091 times 10 to the 8th joules over 750 seconds, which is a power of 545,400 watts. Okay, now let's think about this. That's the amount of power that's actually required for the plane to get from takeoff to cruising, from point A to B. But what we're given is that the plane is actually exerting 1,500 horsepower. So one way to judge kind of how good the plane is doing is to take the power that's necessary, so the power that's needed, and divide it by the power that's actually used. And that'll tell us how good we're doing. So when we do that, we get a fraction of about 0.487, which means that the plane is using about 48.7% of the power that its engines produce. And for a plane, that's pretty good. For many mechanical systems, we would call this perhaps an efficiency. Having an efficiency close to 50% is pretty darn good for most systems. So if anyone tells you that they have a mechanical system that's at 100% efficiency, I would think very carefully before listening to them. Some of the perpetual motion machines that you see, there's all sorts of websites these days about free energy, and it's just not very possible. In fact, it's pretty impossible. So anyways, this is our efficiency, and that's not too bad. So that's a basic explanation of how to calculate power.